Okay, first, thanks to CONCYTEC, Fondesit, and the World Bank for financing this research project. In this presentation, I'm going to talk about characterization of steel slag formed in an electrical arc furnace during steel processing. My name is Renato Valencia. Okay. First, sample collections. During we have five samples. Some sample type 1, type 2, type 3, 1 and 2, and type 4. Okay, so these samples were collected from the furnaces, and the electric arc furnace is charged with 44 tons of scrap steel, and in electric arc furnace, with an electric arc which raises the temperature of the furnace at about 1,600 degrees Celsius is used in this furnace. The vapors leaving the furnace, which are then trapped by filtering system, represent red powders, or type 1 sample, and the slag that remain at the bottom of the furnace here are black slag, and this sample is type 2 sample. And then the liquid that remains in the electric arc furnace is taken to the ladle furnace, where the type 3 samples 1 and 2 are collected, which are the metallized slag and furnace remnants. And then the liquid steel is taken to continuous one process that called continuous casting to form the steel bars. These steel bars have flake laminates in the bars. These flake laminates are type 4 samples. Okay, and then we have 5 samples of 2 of electric arc furnace, 2 of ladle furnace, and 1 of continuous casting. In the total process, 44 metric tons of scrap steel is charged, and to produce 13 metric tons of steel. And the total process takes 38 minutes. 38 minutes. I'm going to focus on the type 1 and type 2 samples from the electric arc furnace. Here we have electric arc furnace control room. Here the red powders or type 1 sample, and these samples type 2 black slags. These 2 samples I studied in this presentation. In the next slide, we have this diagram of the total process that occur in the electric arc furnace. First, this furnace is charging. with scrap steel, and also a light slag containing lime and carbon is is added for the formation of oxides. And then during melting of scraps, electrical energy and chemical energy are used. And electric energy such as the electric arc, and in chemical energy such as the burning of the methane gas or natural gas to add heat to the process. When the scrap is molten around 1600 degrees Celsius, oxygen is injected into the furnace in this process. Which reacts with aluminum, silicon, manganese, phosphorus, and sulfur, and iron. And then during refining, phosphorus and sulfur are removed. And in the slagging, operations are carried out to remove impurities from the furnace. In tapping, once we have the composition and temperature of desired steel, the oxidizers such as aluminum or silicon are added to lower the oxygen content. And then the molten steel is transferred to the ladle furnace, and the process in the electric furnace are carried out again. About characterization of the samples type 1 and type 2, we have in this part the raw sample type 1 is a red powders, and sample type 2 is a black slag sample. In this part, we have EDX and a scanning electron microscope in this image. And in this image, also we have a color mapping where each color represents an exciting chemical element in the sample. The major elements, chemical elements, we have zinc with 59%, iron and 22%, chloride in 10% for type 1. And for type 2, we have calcium 47%, iron in 13.2%, and silicon in 11%. And then we also have Ray Fluorescence of type 1 and type 2. And in the next slide, I have a comparison between Ray EDX and Ray Fluorescence. In elemental chemical composition, EDX show chloride, silicon, potassium, calcium, manganese, iron, zinc, and tantalum. And X-ray fluorescence show more elements: chlorides, silicon, potassium, calcium, chromium, manganese, iron, copper, zinc, and others. But the difference is in the amount of elements is due to the inhomogeneity of the sample and the penetration length of each technique on the sample. Also, the analysis area of Ray fluorescence is larger than EDX. In the next slide, we have the Ray diffraction of type 1 sample, the red powders. And in this sample, we have zinc oxide, magnetite, this compound zinc hydroxide chloride monohydrate, and potassium chloride. Why is there zinc oxide? Zinc oxide is used as a protective layer for steel pieces to prevent corrosion. And then zinc oxide is here in this sample. And this compound, zinc hydroxychloride monohydrate, could be related to the corrosion of the zinc aluminum layer that is also used as an anti-corrosive in steel. Is for this compound. In the type 2 sample, the black slag sample, we have magnetite, the calcium ferrite, the calcium silicate, and oxide manganese. We have compounds with calcium carbonate, with calcium in these two compounds. These compounds, in calcium carbonate and calcium oxide, it is used to separate the steel from scrap, and also to protect it from elements of the environment. And then to form this compound, the calcium ferrite, this compound forms around 700 degrees Celsius by reacting these two compounds, carbonate calcium plus hematite. And for the calcium silicate, this compound form at temperatures around 1415 degrees Celsius by reacting calcium oxide plus quartz. The compounds. Okay. And this is about Ray diffraction. We have these phases in the samples, type 1 and type 2. And in the Mössbauer spectroscopy, we have doublets. One iron 2 plus, other iron 2 plus, with quadrupole splitting 0.95 millimeters per second, and 0.71 millimeter per second. These doublets is here. And in magnetite, we have two sextet, and side A, first side is iron 3 plus, another iron 2 plus, and iron 2 plus, with hyperfine field 48.69 Tesla and 44.59 Tesla. And these sextets are here, and this sextet is hematite. these phases no we have no in a Ray diffraction not see this element in a Ray diffraction, and this sextet have 52.18 Tesla, and this is about sample type 1, that is the red powders. In the type 2 sample, we have the same two doublets, iron 2 plus and iron 2 plus, and the two sextets of magnetite, and this compound that in Ray diffraction also appear in this technique. And we have two sextets of iron plus 1, and one is iron plus 1 and other is iron 2 plus with hyperfine field 15.8 Tesla and 43.5 Tesla. And the doublets are here, and magnetite is two sextets, and the calcium ferrite are here, these two sextets. And okay, in the next slide, I have magnetic properties. This curve is long moment versus external field. And one curve is for 5 Kelvin, the black color, and other for 115 Kelvin and 300 Kelvin. And in this figure, we have the center of this curve, a sum of this curve between minus 4000 to 4000 Oersted, and is clearly observed that has in 5 Kelvin is more clearly the hysteresis loop, and in this loop we have extra coercive field equal to 242 Oersted, and in others temperature in 115 Kelvin or 300 Kelvin, the coercive field is very small. But this sample due to the existence of magnetite in this sample, we show a hysteresis loop, and this is a behavior, for ferromagnetic behavior. And then in the next slide, we have log moment versus temperature, a zero field cooling and field cooling for both external fields, 500 Oersted and 1000 Oersted. And in the zero field cooling curve here at 1500 Oersted, a transition about 25 Kelvin here is observed that could be due to the contribution of all the phases in the sample to the long moment, or it could be a Berwick transition that has shifted to a lower temperature due to the small size particle. This for sample type 1. And in the sample 2, we haven't a hysteresis loop. In this figure, we have a magnetic remnants of the squid equipment, but no, and it's not a. There is no coercive field. This sample, this magnetization curve indicate that apparently the sample 2 is superparamagnetic and not ferromagnetic, because in this sample we have magnetite. About magnetic properties of long moment versus temperature in type 2. The same in 500 Ørsted and 1000 Ørsted. In 500 Ørsted, we have in zero field curve 2 transitions at 49 around 49 Kelvin and 114 Kelvin. These transitions, about 25, could be due to the contribution or okay. The 114 Kelvin could be the Berwick transition of magnetite, because in this sample we have magnetite. The Berwick transition is around 125 Kelvin. But in other transition, I'm still working on these measurements to determine what causes the magnetic phases transition in this sample. Also, I need to understand the superparamagnetic behavior of the type 2 sample. Conclusions. In conclusions, the process that occur in the electrical furnaces were described, and it was found that the major components are iron, zinc, and calcium, with an energy dispersive X-ray and X-ray fluorescence. The Ray Diffraction shows that both samples have magnetite as a mineralogical phase. Mössbauer Spectroscopy determined that there is hematite in the type 1 sample, and in the squid magnetometry, ferromagnetic behavior is observed in the type 1 sample, while the other measurements require further analysis and discussions to determine what the magnetic transition and the superparamagnetic behavior of the type 1 and 2 samples are due to. Okay, that's all. That's all. Thanks to CONCYTEC Foundation and the World Bank for financing this research project. And that's all of my presentation.
Okay, thank you very much, Renato. Thank you very much for your nice talk. Now we are going to start with the questions. Professor Relian, do you have any question? Your microphone, Professor Relian Zhang.
Yeah. Hi. Yeah. Thank you. My question is, you study the magnetic properties of this slag. we find any interesting magnetic properties which can be useful?
En las propiedades magnéticas, ¿qué interesante has encontrado? Repite.
¿Qué interesante encontrado?
Sí. Muestra las gráficas y muestra qué cosas interesantes has encontrado.
Okay, in type 1 sample, we found that this sample is ferromagnetic. It's a ferromagnetic sample, and in long moment versus temperature, we have a transition that could be a Berwick transition, but this Berwick transition is shifted at low temperatures because we have a small size particle. It's a hypothesis. And in type 2 samples, this curve apparently is a superparamagnetic. This curve is this sample have a superparamagnetic behavior. And then the particle size of this sample is very small. It's nanometric particles. And in long moment versus temperature, we have two transitions that I need more more information about these transitions. But the transitions about 114 Kelvin could be a Berwick transition of magnetite. This is about magnetic properties of sample type 1 and type 2.
Okay.
Renato, voy a explicar esa parte. Déjalo ahí en esa gráfica, voy a explicar. Delian, apparently in that plot, that is the magnetization in the y-axis versus the temperature. It's at low temperature. There are two loops. One it is zero field cooling and then field cooling. Set FC and FC, zero field cooling and field cooling. Okay, in the zero field cooling means that without a field, without an external magnetic field, the sample is cooling down until 10 Kelvin, roughly 5 Kelvin or so. Then increasing the temperature, and we measure the magnetization. And then in the field cool, we come back. Okay, the situation there is Renato has pointed 2 points, 114 Kelvin. The red one is obtained at 500 Oester low applied field. The blue loop is at 1000 Oester applied field. Okay, the red one is, you can see two arrows. One arrow 114 Kelvin. That is near the Berwick temperature. What is the Berwick temperature? The Berwick temperature is the temperature of transition of the magnetite. Magnetite has a transition around that temperature. It changes structure, magnetic structure changes. If that appears in the loop, it means that the sample has magnetite.
Okay.
So even that it is in low amount, it has magnetite. Why in the blue line does not appear? Does not appear because the applied magnetic field is strong. When the applied magnetic field is strong, the other components has more strong magnetic signal, and the magnetite signal is hidden. So at low applied field, you can see that. At high applied field, you cannot see that. You understand?
Okay.
That is yeah. And maybe the 49, it is because iron are reacting maybe with silicates, some silicon iron oxide, some silicate iron oxide. That is Renato trying to say. Because it's a mixture of iron oxides, a mixture of calcium, carbons, and so many mixture of many. It's a slag, and there are many magnetic components that interact between them. Okay. Yeah.
Okay. Okay.
Thank you. Thank you. Thank you, Renato.
Okay.
The next question.
Okay.
Please.
Yeah, Professor Angel Bustamante, question.
Yeah, see, there is two questions. Renato, please show to me the lámina 9, no, lámina of diffraction, X-ray diffraction. Lámina this is see, you see X-ray diffraction, there is many residual components or spurious components, maybe, no? Por ejemplo, show to me lámina 10, 10, lámina 10. Por ejemplo, in this type, I see double two blue color. Mathematical is correct for the fitting, but physics, in terms of physics, I don't know. No. Maybe do that. I do that. Because in this case, you need to measure to low temperature, Mössbauer low temperature.
Okay.
Because the assembly here is very, very long after on the left. No, it may be to the correct double maybe is Einstein at the it's typical to superpermanent behavior. When you measure
Ok, Renato, ¿puedes responder?
Escuché recortado las últimas partes.
Que Ángel tiene su micrófono medio mal y cuando tiene que estar todo el mundo callado como para que él se le pueda escuchar.
Okay. But in Mössbauer spectroscopy, I believe that it's necessary a measure in low temperature to observe any properties of some compound.
Talk to me the lámina 10.
Then?
Ok, ¿puedes comentar algo al respecto a este, Renato?
Okay. In Mössbauer spectroscopy, with discussion with Dr. Marlon, we believe that a measure in low temperature is necessary to understand and understand if in these samples there are small size particles, because in slide 14 we have apparently superparamagnetic behavior, and if this temperature is a Berwick transition, it's because we have a small size particle in this sample.
Okay, Renato, let me interrupt there. Renato, in the magnetization versus temperature, magnetización versus temperatura, tipo 1, yeah, apparently that is not the Berwick transition. I know that Berwick transition is 118 roughly.
I can hear you.
Okay, however, yes, there are some reports that the Berwick transition changes because a little because the size of the grain, but apparently not is the case there. Apparently, it is not super paramagnetic there. Apparently, because it is not sure, because there is not a blocking temperature there. There, what is indicating there that if there is a Berwick transition, it is very hidden at that signal. We need to apply maybe a 100 Wester if we could see, or 50 Wester apply field if we could see the Berwick transition. At that 500 Wester, the applied magnetic field is quite strong for the sample that the other components are strong enough to screen the Berwick transition. If there is Berwick transition, maybe there is not Berwick transition. Quizá no haya transición de Berwick, quizá. You understand? ¿Entiendes? Pero eso de ahí, el 25, no creo que sea Berwick transition. No. Y no aparece, no parece que no es tampoco composite, because there is not a blocking temperatura de bloqueo, no está apareciendo ahí. Parece ser.
Luis,
sí.
Luis,
Sí,
remember, there is another small phases. At the low temperature, one, this is spurious phases, show to magnetic behavior, because you in blue curve you have to reduce the continuous increase behavior is now is reduced. No, the dependent tangent is increased, but in this part you reduce. Understand? Because to another and this temperature there is some behavior from I don't know what sample is the ferromagnetic or antiferromagnetic behavior. In the lamina 14 show more clear. Muestra el siguiente, Renato. Interesting behavior. Muestra 14. No, show el 14. Pasa al 14. No, 14. Ahí se ve más claro. 14. Mira, ¿ve? Hay que compare this part and this part. Maybe something other points.
Sí, ahí sí podría haber tamaño de nanopartícula. Ahí podría.
No, Luis, mira a ver. Sí. Aquí incrementa. La tendencia incrementa. ¿Ya? Y aquí va a disminuir más. ¿Te das cuenta la relación? En el otro caso, aquí disminuía. Y aquí recién incrementaba. ¿Te das cuenta? Cuando comparas los dos. Compara esta parte con esta y en la otra lámina también vas a darte cuenta. La tendencia aquí ya incrementa más, favorece al campo, o sea, es ferromagnético, pero cuando reduce, antiferromagnético, ¿te das cuenta? Bueno, ese es my idea. Thank you.
Okay, thank you, Ángel Bustamante. Thank you. Okay, any other question from the public?
Luis, I would like to say something.
Go ahead.
Well, actually, we have technical problem with Mössbauer measurement, but I think in the next week we could resolve this technical problem, that technical problem. But I think Mössbauer measure at the low temperature is necessary, like Professor Bustamante told him. Well, I think that's all.
Okay, thank you very much. What about the measurements at low temperature of the Mössbauer? Is complete or not yet, Marlon?
It's not yet, still.
Okay. And what about from
because
the
one pieces were broken. Was broken when we measure at low temperature. Actually, we have this problem. I don't know if the next week exactly we could resolve this case, but I think they are thinking to import these pieces, to buy and import these pieces.
Okay, thank you very much. Thank you. Any other question from anybody? If there is no more question, thank you very much, Renato, and we are going to continue with the meeting, okay?